Welcome back. So in this video, we want to ask the following question. If f is a continuous function defined on the closed bounded interval from a to b, then how do we define the average value of f on this interval? So to answer this question, we need to think about, how do we go about defining the average value of a continuous function? We know what average means when we have a discrete set of values, right? If we have 10, 20, 30 values, we know how to take their average. But when you have a continuous function, how do you find the average, or how do you even define it? So the idea is the following. So we have the so we want to find the average value of f on the interval from a to b. So let's say that the interval from a to b is drawn right here. So let's say that this is a, and let's say this is right here is b. Okay. So the first thing we want to do is divide the interval from a to b. So we want to divide the interval from. So we want to divide the interval from a to b into subintervals of the same length. So let's say that we divide this interval from a to b into subintervals, and we partition it at the points x0, which is a, x1 is right at this point, x2 would be this point right here, and dot dot dot, xi minus 1 here and xi here, and the last point here, b, is xn. So we have partitioned basically the interval from a to b into n subintervals, and so when we have n subintervals, so this is the interval from x0 to x1. That's the first subinterval. The interval from x1 to x2, that's the second subinterval, and so on. And generally, so since I want to talk about one of them, one of these subintervals, so this is the ith subinterval, where I is between 1 and n. So this is the ith subinterval. It'll be between xi minus 1 and xi. And so now, so again, we have divided the interval from a to b into smaller subintervals. Now, and the length of each of these subintervals is equal to, so delta x is the length of each of these subintervals, and it is equal to b minus a over n. So b minus a is the length of the entire interval from a to b, and then we're dividing that by n to get the length of each of these subintervals, because we are partitioning it. We are partitioning the interval from a to b into intervals of the same length. Okay, so now we pick a point x1 star within the first subinterval. Then we pick x2 star within the second subinterval, and so on. We pick xi star within the ith subinterval, and within the nth subinterval we pick xn star. So we pick a test point in each of these subintervals, and so then basically we are picking n points from these subintervals. So now what I'm going to do is I'm going to say, okay, the average value of f is going to be approximately the average value of f at the test point. So I can evaluate f at each of these test points and add them and then divide that by n, because we have n points here, and we evaluate f at these n points and we add them up and we divide by n. So this is basically f of x1 star plus f of x2 star plus dot 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 plus f of xi star plus dot 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 f of xn star. So we are taking the sum of the values of f at these test points, and then we are dividing that by n. So now let's rewrite this sum. So what is 1 over n? Well, if you see, delta x is equal to b minus a over n. So 1 over n would be delta x divided by b minus a. So 1 over n is the same as delta x over b minus a. Now I'm going to push the delta x inside of the sum. So I get 1 over b minus a times the sum I going from 1 to n of f of xi star times delta x. Now if you recall, this is exactly the Riemann sum of the function f. So we know that as n goes to infinity, this Riemann sum is going to approach the definite integral of f from a to b. So then we see that the average value of f on the interval from a to b would be equal to 1 over b minus a times the integral from a to b of f of x dx. So the definition of the average value of f on the interval from a to b is given by the limit of this sum. So if I take the limit of this sum as n goes to infinity, that's the definition of the average value of f. And then we know that that approaches the definite integral, so the average value would be equal to 1 over b minus a times the definite integral from a to b of f of x dx. All right, so we're going to apply this formula then to find the average value of a function. So if f is continuous on the interval from a to b, then the average value of f from a to b is given by this formula. Let's apply it. Let's find the average value of this function over the interval from -2 to 3, and it is going to be 1 divided by 3 minus 2. So that's the length of this interval. The length of this interval will be 3 minus 2, which is going to be 3 plus 2 and 1 over 5 here. And then we integrate the function f from -2 to 3. And so this is 1 over 5, and then the antiderivative here would be 6x to the 3 over 3, which would be 2x cubed. This would be 2x squared over 2, which would be x squared. And the antiderivative of 1 is x. So -2 to 3, plug in 3 and -2. So if I plug in 3, I get 2, 3 cubed minus 3 squared plus 3. Minus, if I plug in -2, I get 2, -2 cubed minus 2 squared plus minus 2. And we do the arithmetic and simplify. We get 14. So the average value of f is 14. And here is the graph of this function f from -2 to 3. And you can see the 14 right out here. So 14 is the average value of this function. Notice that if we multiply the average value 14 with the length of the interval from -2 to 3, the length is 5. So if I multiply 5 and 14, you can check that that's going to be the area, the shaded area here, that is the area below the graph of f from -2 to 3. By the way, that area is simply given by the integral from -2 to 3 of f. So if I integrate f from -2 to 3 without this factor here, then that integral is going to give me the area below the graph of f from -2 to 3, and that's going to be 70. All right, so another example. So g of x is 17 e to the 0.05x. We want to find the average of that from 20 to 30. So the g bar, or the average of g, is 1 over 30 minus 20 times the integral from 20 to 30, 17 times e to the 0.05x dx. Now the antiderivative, to find that, we're going to use u to be 0.05x, du would be 0.05 times dx, and so in this case I'm going to multiply both sides by 20, or you can say we divide both sides by 0.05. If I do that, then I get 20 du is equal to dx, and then so we get, here I get 1 over 10, 17 can be taken outside, 20 du is dx, so dx is replaced with 20 du, and then this is e to the u. 17 was taken out already. And then the limits of integration, so when x is 20, u is, what is 0.05 times 20? Well, that's 1. So when x is 20, u is 1. And when x is 30, u would be 1.5. So we get the antiderivative here is e to the u. So right here we get 34. So 34 e to the u is the antiderivative. Plug in 1.5 and 1. And this is what we get. And we can rewrite that as 34 e to the power, this is 3/2. So that's the same as the root of e to the 3 and minus e. All right, so that's the average value. And if you look at the graph of this function g of x, that's here, and then between 20 and 30, that's the graph here. And the average value is 34 root of e cubed minus 3e. You can approximate that by using your calculator, but that's about right here. And then you can see that the area of the shaded region would be the same as the average value multiplied by the length of this interval from here. So 10 times the average value would be the shaded area. Again, that's because this integral right here, that's the area below the graph of g, above the interval from 20 to 30, right? So that's the meaning of this integral. And then we are dividing that by 10 here. So obviously the average value multiplied by 10 would be the same as this integral right here. So if I multiply the average value by 10, then I'm going to get this integral, which is the area below the graph of g. Okay. Let's do another example. So let's say a yeast culture is growing at a rate of W prime of t is equal to 0.4 e to the 0.2 t grams per hour. So this is the rate of growth of the yeast culture in grams per hour. The culture's total weight gain during the first 5 hours. So this is the graph of this W prime of t, and the culture's total gain during the first 5 hours is the area between the graph of W prime and the t-axis over the interval from 0 to 5. Okay, so we know this area right here represents the total weight gain during the first 5 hours. And how do I find that? Well, so basically this is the rate, right? So if we integrate the rate, we get the net change in the weight. So this is the rate of weight. So we integrate from 0 to 5, the rate of weight here, then we're going to get the net change in weight. And so if we integrate that, the antiderivative of this guy, you can find that it is 2 e to the 0.2 t. So I'm not showing you the work here. You can do a u substitution. But this is the antiderivative here. So now you plug in 5 and 0, you get this, and that's 2 times e minus 1. So that is the weight gain over the interval of time from 0 to 5. The culture's average weight gain during the first 5 hours, what is that? Well, the average weight gain during the first 5 hours would be 1 over 5 minus 0 times the integral from 0 to 5 of 0.4 e to the 0.2 t dt. So this is the rate of weight, or w prime here. And we already calculated that integral. And so this is going to be, so the value of this integral we calculated to be 2 times e minus 1. So now it will be 2/5 e minus 1. That's about 0.6873 grams per hour. So the average weight gain would be this over the first 5 hours. Okay, and then in the picture you can see the 0.6873 is right about here. So once again, okay, so let me pause here for a second for you to look at this picture again. So again, we started with this example right here, where the rate of weight was given by this, and so notice that so in right here we found the average value of the w prime of, so this integrand here is w prime of t, that's the rate of weight. So this is the average rate of weight, right? So this is the average rate of weight that we found here. So let me make that clear. Okay. So this is the rate of weight, and then the average rate of weight is right 0.6873. Okay, so now let's find the culture's average weight gain during the second 5 hours. Second 5 hours means hour 5 to hour 10. Well, in that case, we get 1 over 10 minus 5, the integral from 5 to 10 of 0.4 e to the 0.2 t dt. And then if we calculate that integral, we end up with 1.8683 grams per hour. So the average rate of weight is given by this. So the average weight gain rate is this. So in the second 5 hours, the weight of the yeast is increasing at this rate on average. And in the picture, you could see that we're going from 5 to 10. Then the average rate is about 2. All right, so this is it. That's the end of this slides. And so this is it on chapter 5, I believe. In the next video, we will be looking at computing area between curves. So area between two curves. So how do we find the area between two curves? That's the topic of the next video. All right, I'll see you in the next video. Thanks for watching.